Hello to everyone, I'm Pablo Escribano and I'm going to tell you about this work in which we generalize the Scotogenic model. Here we computed the neutrino mass matrix and we studied the high energy behavior of the model. So let me start. Everyone here is tired of hearing that the standard model is an incomplete theory and that it must be extended. So I will not delve further in the issues that it presents, but I'm going to remind you two of the most important ones. First, the experimental observation of neutrino meso and of neutrino flavor oscillations, implying the existence of a mechanism that accounts for neutrino masses and mixings, and also what is the nature of the dark matter of the universe. So, following this line, many models have been proposed along the years, but one appealing possibility are radiative models. And what makes radiative models interesting is that the suppression introduced by the loop factors allows one to accommodate neutrino masses and mixings with large Yukawas and relatively light mediators. Also, if these models include discrete symmetries connected to the radiative origin of neutrino masses, we can have viable dark matter candidates, resulting in very economical setups. And one of the most popular radiative models proposed to generate neutrino masses is the Scotogenic model. This model, with only the addition of 3 singlet fermions and 1 scalar doublet, as well as a dark Z2 parity under which all the new particles are odd, is able to simultaneously induce neutrino masses at the one loop level and also to obtain a weakly interacting dark matter candidate. Since the appearance of the model, many variations and extensions have emerged, and they include, for example, colored versions of the states, or they use additional states or symmetries. However, here we wanted to introduce the general Scotogenic model with an arbitrary number of generations of the Scotogenic states. So we will have an arbitrary number of nn of singlet fermions and also an arbitrary number n eta of scalar doublets. Now, since we are focused on computing the neutrino mass matrix in the general setup, the relevant terms in the Lagrangian are these ones, which are the Yukawa and the Majorana mass terms. Here we have the Yukawa tensor, and here MNN is a symmetric Majorana mass matrix, which is chosen to be diagonal without losing generality. So now regarding the scalar potential, it is on here, and this lambda 5, which is probably one of the most important parameters in the model, is a symmetric matrix. These lambda 3 and lambda 4 are Hermitian matrices, and m eta squared is chosen to be diagonal without losing generality. Okay, so now, assuming that the minimization of the scalar potential leads to this vacuum configuration, we will have the electroweak symmetry to get broken in the standard way, and the Z2 symmetry will remain unbroken, ensuring the stability of the lightest Z2 charged particle. Now, for the sake of simplicity, we will assume that all the scalar potential parameters are real, hence conserving CP in the scalar sector. This way, the real and imaginary components of the neutral scalar doublets do not mix, and we can write them this way. Now, after electroweak symmetry breaking, the CP even and CP odd scalar mass matrices can be written this way, where we note that in the limit of lambda 5 going to 0, both matrices are the same. And this is an important point for the derivation of neutrino mass of the neutrino mass matrix. And it will also be important to obtain the change of basis matrices from mass to gauge scalar eigenstates, which are these B's here. And since all the scalar parameters are real, the V matrices are orthogonal. Now, the V matrices depend on the scalar parameters in a non-trivial way, so it is better to simplify the results using these assumptions, which are shown here. And under them, the scalar mass eigenvalues take this simple form. And regarding the V matrices, they can be written as a product of several rotation matrices, whose angles are given by this expression. Okay, now we are in position to talk about neutrino masses, and they are generated by these loop diagrams, shown here, exactly as in the original Scotogenic model. And the amplitude of this diagram is shown here, where we have introduced the C factors, which are the couplings between the neutrino, the neutral scalars, and the singlet fermions. and the expression is shown here. And now notice that several diagrams contribute to the neutrino mass matrix. We will have one for each real and imaginary component of the neutral scalars, and also one diagram for each singlet fermion and scalar doublet generations. So after some algebra computing the amplitudes of the diagrams, we can get to this exact neutrino mass matrix, where this B0 is the standard Pasarino-Bellman function, which is on here, and this this divergent part cancels exactly as expected. So now we have the exact neutrino mass matrix, which is shown here. It looks great. It's very simple and elegant, but only in appearance. It involves a product of V matrices and loop functions, both depending on the scalar potential parameters in a non-trivial way. So it is better to approximate the neutrino mass matrix by expanding in powers of the lambda 5 parameter and also in powers of the small parameter s, which is shown here, and it is nothing but the sinus of the scalar mixing angles. And also to make the expression simpler, we have defined this gamma tensor and the loop functions f and g. And finally, we have checked that the approximation the approximation reproduces the exact neutrino results, the exact neutrino mass matrix results in a good approximation. Okay, so now we wanted to study a crucial point for the Scotogenic setup to be consistent, which is the breaking of the Z2 symmetry. And this is also known as the parity problem. So what happens is that the RGE flow can alter the shape of the scalar potential at high energies and lead to the breaking of the Z2 symmetry. And in the absence of the symmetry, neutrinos would acquire masses at tree level, and the dark matter candidate would no longer be stable. So we can understand some features of the high energy behavior by inspecting the one loop beta function for m eta squared. So it turns out that the negative contribution of the trace term, this one, will be crucial for the breaking of the symmetry. So for large Yukawas and singlet masses of the order or above the scalar mass, the trace term dominates the running, driving it towards negative values. And once the mass becomes negative, the scalar acquires a non-zero BEV and the symmetry gets broken. So since we can't study the high energy behavior of the model in the general version, we will concentrate on two versions of the general model, which are the 3-1 model, which is nothing but the original Scotogenic model, and the 1-3 model, which includes one singlet fermion and 3 scalar doublets. So what we do is to set all the parameters at the electroweak scale, but always to values that guarantee that the scalar potential is bounded from below. And also we have to keep in mind that we must accommodate the neutrino square mass differences and mixing angles observed experimentally, but this can be done by means of an adapted Casasibarra parametrization to the models we are focused on. So now, before going to the numerical results, I wanted to say that while several phenomenological directions of interest can be followed here, we are interested in the effect of the trace term. So this motivates us to use very small lambda 5 parameters and also Yukawas of order 1. Okay, so now first we wanted to recover the parity problem mentioned before, and it is shown here in these plots. So on the left, we have for the original Scotogenic model, the CP even lightest scalar mass. Well, sorry, the CP even scalar mass. In the original Scotogenic model, we have only one scalar doublet. And the mass is displayed as a function of the energy scale mu. And we can see that the mass eventually becomes negative and the scalar becomes tachyonic. And this is a clear sign that the particle has acquired a non-zero PEV. And this breaks the symmetry. And also we see a drastic change in the evolution of the mass when the heaviest singlet becomes active, which is at about 2 TeVs. And now on the right side, we have for the 1-3 model, the 3 scalar masses displayed at the same time, although the lightest scalar mass would be the minimum of the 3. So now again, the lightest mass becomes negative, breaking the symmetry, and the change in the behavior happens when the singlet becomes active at about 8 TeVs. And now we are going from now on, we are going to focus on the 1-3 model, since the other one has been extensively studied. So here we have represented the Z2 breaking scale as a function of the singlet mass, and we have displayed this breaking scale for 3 different parameter sets. So, as expected, the symmetry breaking scale decreases for larger singlet masses because the effect of the trace term becomes stronger. However, for the green curve, below masses for the singlet of 2 TeVs, about more or less, the symmetry is not getting broken. And we will understand this in a moment. So now what we are going to do is to focus on this set of parameters, and we are going to represent the lightest scalar mass as a function of the energy scale for several singlet masses. Sorry. So now for the for a singlet mass equal to 2.2 TeVs, we see that the mass starts decreasing and eventually it becomes negative, again breaking the symmetry. However, for lower values for the singlet mass, this is not happening. Indeed, the lower the mass is, the faster the scalar mass goes to infinity. So what is happening is that at the beginning, the mass starts decreasing. This is because the trace term is dominant. And then eventually at higher energies, the mass starts increasing. And this is happening because a Landau pole is appearing in the lambda 2 quartic coupling, and it is preventing the symmetry to break. However, at some point here at high energies, the theory becomes non-perturbative, so we can take too seriously what's happening here. And finally, just to conclude, I wanted to say that our generalization offers several phenomenological possibilities as LHC signatures. And for instance, the eta doublets can be produced at the LHC due to their couplings to the standard model gauge bosons. And this can initiate cascade decays that can lead to striking multi-lepton signatures, including missing energy due to the production of the lightest Z2 charged particle. And this brings me to the summary of the talk. So in this work, we have presented a generalization of the Scotogenic model with to any number of generations of the VSM particles. And after computing the one-loop neutrino mass matrix on the general version of the model, both exactly and approximately, we have studied the high energy behavior of the model, focusing on 2 specific variants. And our main conclusion is that the features of the original model are present in the multiscalar version as well. And also, our generalization offers several phenomenological possibilities, like, for instance, the production of the eta doublets at the LHC due to their couplings to the standard model gauge bosons that can initiate cascade decays, leading to striking multi-lepton signatures. And also, the dark matter production rates might be affected by the additional scalar degrees of freedom. And that's it. Thank you very much.